In this last section of Homework 6, we're going to look at logical arguments. Now, an argument is made up of two parts. First part, or parts, are called premises. You may have one or more. Usually you have more than one. We're going to stick in our examples with just a couple. The premises are the things that we're going to assume are true, and our desire is to find out if those premises lead to the second part, which are our conclusions. You can have one or more conclusions, though in our examples we're going to probably stick with just one conclusion, though sometimes there are more. So we're not really asking, when we look at an argument, are the premises true? We're assuming that they can be proved. Okay? If they can't, then your argument is gone anyway. Okay? But we're assuming if the premises can be proved, is the knowledge that they're true enough to guarantee that the conclusion is also true. So we're asking if our premises lead to our conclusion. So we can do this one of two ways. We can use the truth tables, and we'll take all our premises and AND them together. So I'm going to call the premises P. So say premise 1 and premise 2 and premise 3, or however many premises there are, etc. We AND them together and then imply the conclusions. And we're going to stick with one conclusion mostly. We'll have 2 or 3 premises mostly. But if I had more than one conclusion, I would AND those as well. So we're going to make the argument if premise 1 and premise 2 and premise 3, then the conclusion. And we want to know if that's going to logically lead to the conclusion. Okay. So when we do a truth table, 3 things can happen. We can have all falses, which is called a contradiction. In that case, it would be impossible for all the premises to be true at the same time as the conclusion. Okay, we could have some true and some false. Maybe I should make the true capital. Some true and some false. And I don't know a name for that. Or we could have all true. All true is called a tautology. If we have a tautology, the argument is valid. Okay. If we have a tautology, then the argument is valid. Otherwise, it is invalid. Okay, so one way to determine the validity of an argument, in other words, if it's valid or invalid, which is the same thing as asking do its premises lead to its conclusions, is to make a truth table. Once you find an F in that last final column of your truth table, it's invalid. Okay? So the only way that it's valid is if every single value in that last column of your truth table is true. In other words, it's a tautology. The other way to decide if an argument is valid requires less writing but more thinking. We have 2 kinds of arguments that we're looking at. One of them is a direct argument. We're saying if P implies Q, and we also have P, then we know Q. In other words, if we think about it, if I have P, if I know I have P, and I know that if I have P, I also have Q, then knowing these two things together, I know I have Q. So I'm just following the line of what I have. The other one we have is that if P implies Q, and I have not Q, then I have not P. This comes from the fact that the contrapositive is the same statement. What's the contrapositive of P implies Q? Is not Q implies not P. So here in this one I really have three premises. This one is really the same as this one. But I know I have not Q, and I know having not Q then leads me to having not P. These two arguments actually have names in logic. This one is called modus ponens, and this one's called modus tollens. There are a few other arguments we could use as well, but we're not going to go into them within the scope of this course. So you can use those arguments. If you try and go the other way, then you have errors. In other words, if I was to have P implies Q, and then say I have Q, therefore P, that is not a valid argument, because I know nothing about what if I have Q. That is assuming that the converse is the same, and it's not. If I have P implies Q and I have not P, and I think that implies not Q, I'm also wrong. That is invalid as well. That is assuming that the inverse works. It's the same as the original, and it does not. So we actually call this first one a converse error, and we call the second one an inverse error, because they are not the same. So we'll look at a couple of examples using both the truth tables and the argument method, the modus ponens and tollens, to determine if an argument is valid or not. Okay, the first example we're going to look at is if it rains, then Jerry cries. Jerry cries, therefore it rains. These two are our premises. So I have two premises in this case and one conclusion. The premise is raining implying crying. The second one is crying. And the third one, or the conclusion, is therefore it rains. Okay, if you look at the argument view, you can see, raining implies crying, and I know I have crying. Does that help me with anything? No, it doesn't help me with anything, because the contrapositive would be not crying implies not raining. So I kind of have those three premises. So I can tell from looking at this that this would be a converse error and that this is an invalid argument. I had to think a little bit, but I could figure it out using those arguments. If I want to do the truth table, I've got to take the first premise, R implies C, and what's the second premise? C. So there's my two premises, premise 1 and premise 2. Together I have to see if they imply my conclusion, which is R. So I'm going to have two letters in my truth table, R and C. that means there's going to be 4 levels. True, true, false, false, true, false, true, false. And as I build my table, I'm going to start inside the parentheses with the R implies C. Then I'm going to move out to the R implies C and C. And then I'm going to move out to the final one. R implies C and C implies R. And see if I can come up with my final answer. Remember, if I get any F's over here in this last column, it's invalid. So let's try. True implies true, because I'm doing R implies C. So true implies true is true. True implies false is the only false one we call. False implies true is true, and false implies false is true. I'm now going to take the R implies C column, this column, and AND it with the C column. So true and true gives me true. False and false gives me false. True and true gives me true. True and false gives me false. Now I'm going to do this column implies R. So this column has to be first, that's this column, implies R. Okay, so true implies true is true. False implies true is also true. True implies false. Uh-oh. This one right here leads me to believe that it's not valid or that it's invalid. Okay, if I went ahead and did the last one, it would turn out to be true, but I really didn't have to do that. Once I hit a false, I know that the entire argument is false. So you'll have your option of either way to do these. To write out the truth table, taking the 2 premises, premise 1, premise 2, premise 1 and premise 2, and putting them together and seeing if they give you the conclusion. That's one way. The other way is to look at the arguments and make sure they go in the right order of the 2 ones that we have that work, the original statement and the contrapositive. Okay, let's look at another example. If Fran studies, then she passes the test. Fran passes the test, therefore Fran studies. Again, we have 2 premises, premise 1 and premise 2, and our conclusion. So we'll say studying implies passing. She passed, therefore she studied. We can see that this is also going to be invalid by the same converse problem we had before in the first example. And you can do a truth table in the same way. What would have made this one a valid argument? What if we had, if Fran studies, then she passes. Fran does not pass, therefore Fran does not study. I think this one has more of a chance of being valid. Let's look at it. Premise 1 and premise 2, our conclusion. Studying implies passing, or if Fran studies, then she passes. She does not pass, therefore she does not study. Notice that this is the same as using the contrapositive, not P, implies not S. And we have not P, so we know not S. So we know this one is going to be valid by the modus tollens. But if we do a truth table, the first premise is S implies P, and the second one is not P. So if we put those all together with the and in the middle, and see if that implies the not S. So we have two letters, S and P, and so we have four possibilities, true, false, and true, false. Okay, starting on the inside of this parenthesis, going deep into this one, S implies P, so S implies P is first. Then we've got to do the second one, which is not P. Then we have to put them together. S implies P and not P. Okay, so we've gotten that first parenthesis done. Now we've got to do this one on the right, the not S. And finally, our last step would be the entire thing. The S implies P, and the not P together imply the not S. Remember, if we have an F or false anywhere in this column, then the argument will be invalid. The only way it can be valid is if they're all true. So let's start with S implies P. True implies true is true. The only one that's false is true implies false. So both of these are also true. Okay, now we're going to do the opposite of the P, so we're going to do the opposite of all of these. So the opposite of true is false, the opposite of false is true. The opposite of true is false, the opposite of false is true. Okay, now we're doing and, so we're putting S implies P and not P. So true and false is false. False and true is false. True and false is false. True and true is true. Now we're doing the opposite of S. So I'm going all the way back to the beginning here. And the opposite of S, the opposite of trues are falses, and the opposite of falses are trues. Now I have to go in the correct order. This has to be first. That's this one. Has to be first, implies not S. False implies false is true. False implies false is true. False implies true is true. True implies true is true. Remember, the only one that is false is true implies false. And there isn't one there. This is a tautology because they're all true and is a valid argument. In other words, it's a valid argument if I could prove that these two premises were true, then this one would logically follow. I wouldn't have to also prove it. It would automatically come with the others. Okay, let's put one that has an extra comment in it. If Tanya practices, then she improves and wins. Tanya does not improve, therefore Tanya does not practice. Again, we have just two premises and a conclusion. Okay, Tanya practicing. Let's write them over here. Practicing implies improving and winning. She does not improve, therefore she does not practice. Okay, can we do that using the arguments? Yeah, because this is equivalent to, what's the contrapositive? You have to change it to its opposite, so it would be not I or not W. Implies not P. So in this case it's or. I only have to have one of them. I only have one of them. So I know that it is valid. Okay, so if you can think through it, the thinking through the arguments is the quicker way, the least amount of work. Okay, but if you have difficulty following those, you can always work it out using the truth table. What would our truth table be in this case? P implies I and W, that's my first premise, and not I implies not P. Of course I need to put in some more parentheses here. There's parentheses there, and there, and there. So I'm going to have quite a large table here. I have P, I, and W. So I'm going to have 8 rows. Write small to fit this all in here. True, true, false, false, true, true, false, false, true, false, true, false, true, false, true, false. Okay, let's start on the most inside parenthesis. This parenthesis, and then in here. So I'm going to get down to the I and W. Then the P implies I and W. Then the not I. Then the P implies I and W and not I. The not P. Finally the whole thing. The P implies I and W and not I implies not P. Okay, first of all, let's do I and W. They're right here next to each other, so they're going to be easy to do. I and W, true and true, true and false, false and true, false and false. Remember, the only way that we get a true is if they're both true. True and true, true and false, false and true, false and false. So we only get those two trues. Okay, now we want to do P implies that. So I have to start with the P. True implies true is true. All of these are true implies false. So all of those are false. False implies true. It's true, and all of these are false implies false. So those are true. Remember, the only implication, or the only if-then that is false is true implies false. Okay, now we got to do the opposite of I. So here's the I. Let's do the opposite of I over here. The opposite of the trues are the falses, and the opposite of the falses are the trues. The opposite of the trues are false, and the opposite of the falses are true. Okay, now the next step is calling for P implies I and W, and not I. So these two together. True and false, false and false, false and true, twice. Both of those are false. True and false, twice. So both of those are false. True and true, twice. Hey, those are the only true ones. Okay, now we got to do the opposite of P, so we got to go all the way back to the beginning. The opposite of P, those trues are all going to be falses, and those falses are all going to be trues. And then the final step would be the implication. False, all these are false implies falses. Oops, so these are all trues. False implies true. Both of those are true, and true implies true. So this is a valid argument. A lot of work to do it with the truth table. So if you can work it out with the arguments, you're going to save yourself some work. Last little thing we want to look at is, can we draw conclusions ourselves? Here we have question, what conclusion can you draw? Well, if it flies, so it flies. We don't want to use F because that makes us think of F as in false, so we'll call it S. Maybe for like soaring, I don't know. Flies, then it's a bird and it has wings. It does not have wings. Can we draw any conclusions from that? Well, we can, because we know if we knew S we could do something, but we can also do the contrapositive here. What's the contrapositive? It's the one where we switch it and change it to the opposite. So the B and W will come to the front and become not B, or, because of De Morgan's, not W implies not S. So this is saying if I know either of these, this one or this one, then I know that one. And guess what? This one's saying I know this one, so together I know this one, so I can make a conclusion. It does not fly. It's the only conclusion I can make at this time. Okay, that is the end of our logic, and in the next homework you'll begin looking at the number basis.